Okay, we're going to start off our Circuits 2 lectures by giving a review of calculus. And why are we doing this? After all, in Circuits 1, we talked about devices like resistors, whose voltage across them and current through them were related by Ohm's law, and no calculus is needed. But in Circuits 2, we're going to start to investigate components like capacitors. And for capacitors, there's a relationship between the voltage across and the current through them that does involve calculus. And just like in Circuits 1, we can solve for the other variable by doing the opposite of multiplication, which is division. In calculus, we can solve for the other one by doing the opposite of integration, which is taking the derivative. So let's begin by talking about how we notate taking derivatives. One way we can notate it So let's talk about how we can notate how we take derivatives. One way we can notate it is with the apostrophe sign. And another equivalent way is by using the d over dt operator. And an equivalent way of showing this is with dv dt. Something interesting happens with the units. If our original function was in units of volts, here when you apply the over dt operator, it's pretty clearly taking your original units and dividing it by whatever your time unit is. So that would be volts per second. So these are all in units of volts per second. And the intuition behind that is that the derivative with respect to time talks about how rapidly the voltage changes in time. And another way to express that same idea is that the derivative takes the slope of a graph. So in other words, if we have a graph that starts out looking like this, for instance, this has a constant rate of increase. So perhaps it's a constant value up here. Now in this region, in this time region, there is no increase at all. So it drops down to 0. The slope here is decreasing. So it instantly go down here. And you can see that it's very, very negative here. It's almost, if you were to graph it, it's almost perfectly negative, infinitely negative. But it quickly smooths out to a 0 rate of change. So we might expect that if this is our function of time, then this is the derivative, the time derivative of that. Now when you took calculus, you learn how to take the derivatives and integrals of a huge array of functions. Luckily, there's only a few that are common in electrical engineering. One of the first ones that are common is a constant. We'll call it C. If you're to graph it, it doesn't change. Another that is common is a function that moves up at a constant rate, constant slope of A. Another one that we see all the time, perhaps one of the most common ones, is a decaying exponential. It looks like this. Maybe I lied. Perhaps the most common of all are oscillating waveforms. The omega says how fast it oscillates. The theta is a phase offset that shifts it left or right. If that phase offset is 0, a cosine would begin at 1 and oscillates like this. and it has a similar related function, sine, who, if its phase offset was 0, would begin at 0 before it oscillates. So let's determine for each of these what its derivative is. For the constant, clearly, the derivative of this, it's not changing, it's just 0. The derivative of a times t is a. The derivative of e to the minus at is minus a e to the minus at. The derivative of this cosine by the chain rule is a sine of the same frequency, just scaled, and also by the chain rule, the derivative of a sine wave is a cosine at the same frequency, just scaled. So let's investigate a couple of properties about derivatives that will let you quickly calculate them for more complicated structures. If you have a constant of any sort and you multiply it by a function, then its derivative will be the constant times the derivative of the function. So as an example, if you had 2 e to the minus 3t, the derivative of that would be 2 times minus 3 e to the minus 3t. The next is the rule for summing functions. If you sum an f of t plus a g of t, the derivative is just the sum of the derivatives. If you multiply, you have to use the product rule, and that says the derivative of the product is equal to the derivative of the first times the second plus the first times the derivative of the second. Now in Calculus 1 you learn many other properties, including such things as the quotient rule. We just don't encounter those things commonly in electrical engineering, nor do we encounter taking derivatives of a lot of other functions. So if you know these, if you just memorize these, you'll be in good shape for what we encounter.